Hello and welcome to this video tutorial. We're going to be looking at our electric fields lab. The purpose of this lab is to learn how to be confident with our electric field calculations due to a single point charge at any point in space, and then use the computer simulation to verify our confidence in these results. Let's begin. In order to be able to calculate electric field due to a point charge, we're going to need the following equation. E, that's the electric field magnitude, is equal to K, the charge constant, times Q, the charge, divided by R squared, where R is the distance from the charge to some point in space. Please remember that we are taking the absolute value of the charge, which means any negative charges, we will not account for the negative. Okay. We're also going to get in the hang of drawing what are called electric field diagrams for multiple point charges. So when you have multiple charges and we're trying to find the net electric field or the total electric field, we're going to get in the practice of drawing what's called an electric field diagram. For single point charges, it's pretty easy, and we'll kind of do that as we go. All right, part one, electric fields for a single point charge. A charge of 3 nanocoulombs, and don't forget, ladies and gentlemen, nano, when you see nano, that's times 10 to the negative 9. It's placed at the origin as shown below. What we want to do is calculate the magnitude and direction of the electric field at both point A and then again at point B. All right, let's take a look at how to do this. Okay, again, we're going to be using this calculation several times today, so make sure you understand how to put that in your calculator. First, I'm going to start with the direction, okay, of the electric field. Now, this is a positive charge, so we know that electric fields radiate outward from all positive charges, right, in every direction possible. Okay, so you can see that at point A, the electric field due to the charge would be directed to the right because I'm extending it out from the charge. You can see for point B, the direction is extended sort of up and to the left. Now we can figure out what the actual angle of that charge is by using a little bit of right triangle trigonometry, and we'll need that. Filling out our equation. We're going to go 9 times 10 to the 9 times our charge. Now, 3 nanocoulombs would be 3 times 10 to the negative 9. And our distance to point A, R, is a total of 2 meters. Okay, plug that in our equation, and we will get a value, a result for electric field magnitude at point A at about 6.75 newtons per coulomb. Again, please practice until you're able to. Most students will get this wrong because they forget to square the distance to that point. Okay, using the same equation, we're going to find the magnitude of the electric field through point B. Now we need to find the distance to point B, right? Because setting it up is pretty easy for the beginning. K times Q, it's the same charge, okay? But we have a different distance. We have this distance essentially right here. Okay, now how do we find that distance? Well, we have this distance here, and we have this distance here. Okay, this distance here is in the negative 1.5 direction. This distance here is positive 2. So use Pythagorean theorem on that, 2 squared plus 1.5 squared, square root that. Go ahead and pause the video and figure out this distance here. You should have been able to come up with a distance of about 2.5 meters. Now, at the same time, we should also find this angle that it is going up as well. Okay, now keep in mind, this is the opposite side, that's the adjacent side, so we're going to be using the arctangent equation to find the direction of the vector. Okay, and all we need is the y component over the x component. So we're going to take the arctangent of 2 divided by negative 1.5. Please pause the video and give it a try. Okay, so if we take the arctangent of 2 divided by negative 1.5, we get about negative 53.1 degrees. Negative because it's going clockwise from the negative x-axis. Okay, but 53.1 degrees above that negative x-axis, that's where we're going. And if we were to take the angle from 0 degrees, which is over here on this side, this full angle here, just go 180 minus that. So 180 minus 53.1 is about 126.9 degrees. That's the one I'm going to use. I'm going to use my angle from 0 degrees. Okay, try to get in the habit of using your angle from 0 degrees. It'll make it for easier calculations when we have multiple charges. Okay, so finish filling this out, and we have about, so what, 2.5? Okay, and we get a calculated or expected electric field at point B at about 4.32 newtons per coulomb. Okay, now is where we're going to use the computer simulated app to actually check and verify not only the direction, okay, so the direction on this one is at about 126.9 degrees. Okay, or you could say 53, or you could say 53.1 degrees above the negative x-axis, right? You could reference it that way too. Either way is fine. Here, this one is it's directed to the right. You can see it would be directed to the right like this. But if you were to reference it as an angle, right, that would be 0 degrees. So 0 degrees is directed to the right. So let's take a look at the actual app and verify some of this. Okay, and we're going to get a measured electric field at point A and B by placing a sensor, electric field sensor, at that point and at that point. Okay, first thing I'm going to do is I'm going to create the, let's go ahead and create the charge at the origin. So I'm going to go ahead and put, I guess I'll make the origin, I don't know, I guess maybe right here. All right, so I need to stack 3 of these charges on top. 1, 2, 3, just like that. I'm going to go ahead and turn off the electric field just for now so it doesn't muddy up the picture. Then I'm going to place a sensor at 2 meters. Now you can see every one of these boxes. So this would be a 0.5 meter. That's 1 meter. 1.5, 2 meters. Okay, got that. Now the other one I'm going to do is I'm going to go over 1.5 and then up 2. So 0.5, 1, 1.5, then I'm going to go up 2 meters. Remember, every one of these boxes is 0.5 meter. So from here, I'm going to go 1/2, 1, 1 1/2, 2, just like that. Okay. Now what we're going to do is we're going to go ahead and record the values that are there. Okay, because the electric field and the direction of the field are recorded on the sensor. So looking at the first sensor over to the right, we can see the magnitude is 6.7 volts per meter. Now, volts per meter is the same unit for electric field. It's just another version of the unit as opposed to newtons per coulomb. So you could use either one. The angle is about 0.2 degrees. That's really close to zero. So let's go ahead and measure that. So the magnitude is 6.0 newtons per coulomb at 0.2 degrees. And then the measured electric field at point B is 4.4 at 127 degrees. Okay, and if we just take a peek back, we can see how close that is to our expected calculations. What we're going to do in part 5 is we are going to calculate the percent error, okay, on these values. The percent error calculation, in case you forgot, is taking the absolute value of the actual value, in this case, the actual electric field magnitude, that would be the calculated one, minus the experimental, that's the measured one, divided by the actual calculation times 100. Okay? So we're going to put this into our calculation twice. Okay, so this is at point A. So this is the electric field at point A. This is the electric field at point B. Okay. So throwing that into our calculator, we have the actual value, which was 6.75 calculated, minus 6.70 divided by 6.75, and then times 100. And we're getting about 0.74% error, 0.75% error. That's pretty darn good. Okay, and then similarly, with the electric field at point B, we're going to go 4 point, and if you remember, it was 4.32 is what we calculated. So 4.32 minus 4.40 divided by 4.32. Because we have absolute value bars set up, we do not have to worry about the fact that the numerator is going to be negative. You get to ignore it. And we get about 1.9 percent error. Again, also pretty low. And you should expect pretty low percent errors based upon this as you practice your calculations, because those represent the actual values which you're supposed to get. And then the app will help verify that. Okay, so how would we find the magnitude direction of the force on a proton placed at this point? Well, we're going to use the equation F equals Q times E. Right? We're plugging into that. Keep in mind the direction of the force, that's easy because a proton, if I have an electric field here and I place a proton in the field, electric fields are always directed from positive to negative, you can see the proton, right, would be attracted to the negative side, right, and repelled from the positive side, meaning protons always go with the field. Electrons, on the other hand, would go against the field. So the direction is going to be the same direction as the field is pointing in point A, which is 0 degrees. Okay, now let's fill this out. The magnitude, we need the charge of a proton, that's the elementary charge E, 1.6 times 10 to the negative 19 coulombs, times the expected measurement of the field at point A, which was, we got 6.75 newtons per coulomb. Throw that in your calculator. Okay, and we're getting a value of about 1.08 times 10 to the negative 18 newtons. You could either say directly to the right or 0 degrees. Either way is fine. Okay, part 7. What would the expected magnitude and direction of the force of an oxygen ion placed at point B? Well, an oxygen ion, so what makes an ion? An ion and atoms are all electrically neutral. Okay, oxygen has, you can see from the 8 here, an atomic number of 8, which means it has normally 8 protons and 8 electrons. But from the -2 charge here, we see there are 2 extra electrons, which means this has a charge of 2e. Okay, 2 times the elementary charge, which would be, if we run this calculation, 3.2 times 10 to the negative 19 coulombs. So let's go ahead and repeat the calculation. Different field strength at that point. Okay, we're looking at about 4.32 at point B specifically, and the charge would be about 3.2 times 10 to the negative 19. Okay, and we get a value of about 1.38 times 10 to the negative 18 newtons. Directed at 127 degrees from the positive x-axis. In other words, the exact same direction as the field at that point. Okay. Now, moving on to part 2, this time we have multiple charges. So anytime you have multiple charges, you're going to draw what's called a field diagram. And we want to know, essentially, we're going to start by finding the magnitude and the direction of the field at the origin due to the positive 2 nanocoulomb charge, then at the origin due to the 5 nanocoulomb charge, and then we're going to find the net or total field at that point. So since this is going to be involving what's called a net electric field calculation, all net electric field calculations are going to require a field diagram for you to figure out the overall direction of it. So here's what we do. We're going to call the origin point P. Over to the side, let's draw this diagram. Okay, point P. Now, let's start with this. I'm going to call this one Q1, and I'm going to call this charge Q2. So if you look at what's going on, the electric field goes out in all directions to both charges, just like this. Okay, but now you can see this would be E1, right, sending it out in all directions because it's the electric field from Q1. This would be E2, the electric field from Q2. Now watch what happens. E1 passes through point P going to the right. So we're going to draw that right here. E2 passes through point P going to the left. So we're going to put that one right here. And you can see since E1 and E2 are going in opposite directions, the net field will be calculated by just simply subtracting the two. Okay, and whatever value has the bigger field magnitude, that is the direction that the net field will be going in. So we're basically going to take the direction to be, if your answer is positive, it's going to the right. If your answer is negative, right, it's going to the left. Okay, so let's figure out the individual field magnitude. So E is K times Q over R squared. We're plugging into that. Okay, and we're going to do that twice. Once for both charges. So it's 9 times 10 to the 9 times, now this is Q1, this is Q2, this is R1 squared, this is R2 squared, this is E1, this is E2. Okay, so for Q1, it's going to be 2 nanocoulombs, so 2 times 10 to the negative 9, and you can see it is a distance of 1.5 meters away. Whereas the next one, and we'll go ahead and run that calculation there. And then the next one is going to be, again, 9 times 10 to the 9 times a 5 nanocoulomb charge, or 5 times 10 to the negative 9. And it has a distance of 2 meters away from the origin. Okay, go ahead and run both of those calculations in your, put those in your calculator. Okay, at this point, pause the video and complete both calculations for point A and point B. Okay, so the electric field magnitude at point A should come out to about 8 newtons per coulomb. And at point B, we should come out to about 11.25 newtons per coulomb. So essentially, one way you could do this is you could just go bigger field minus smaller field, and the net field goes in the direction of the bigger field, which is in the direction of E2. So E2 is pointing to the left, so the ultimate net field is going to point to the left since E2 is bigger than E1. But basically, we do have to take the difference of the two. Okay, so essentially the net field is going to be the difference in your electric fields. So let's go ahead and figure that out. We're going to have our net field, and we're going to go 11.25 newtons per coulomb minus 8 newtons per coulomb. And we get a net electric field at the origin of about 3.25 newtons per coulomb directed to the left is the overall direction for the overall field magnitude. Okay. Now, what we're going to do is we're going to do the exact same thing, and we're going to find the measured value of the electric field by placing the charges where they belong and a sensor right at the origin. So let me go ahead and clear this. Need that, need values, need grid. Okay, so I'm going to place, I'm going to call this the origin. So I'm going to go over 1, 2, 3, right about there. I'm going to place 2 nanocoulombs right there. Okay, then I'm going to go over 1, 2, 3, 4. I'm going to go 5 nanocoulombs there. So I'm going to stack 5 charges on that one. 1, 2, 3, 4, and 5. Okay, and then we're going to place a sensor right at that origin, and let's get a feel for the net total field. And you can see the value that we're measuring here is about, the direction is negative 180, which is directly to the left. 179.8 is almost 180 directed to the left. And about 3.14, right, is our measure. Pretty darn close. Pretty darn close at essentially negative 180 degrees would be directed to the left. So ultimately we are getting some good consistency with our calculation. Let's go ahead and complete our percent error calculation on this. Absolute value of our expected is 3.25 newtons per coulomb minus 3.14 newtons per coulomb divided by 3.25 newtons per coulomb, then multiply that times 100. And we get about a 3.4% error. Okay, pretty darn good. Number 6, what is the magnitude and direction of the force of a proton placed at that right there? We're going to use the equation F equals Q times E. I will let you finish this one out yourself. What would be the magnitude and direction of a force of an oxygen ion? Remember, an oxygen ion has a charge of 2e, like we did earlier, placed at point B. Okay, again, I will let you go ahead and try this calculation yourself. Okay, part 2, the continuing part of part 2, this really should be part 3. We have the identical charges placed exactly as far away, and we have point P placed 2 meters above the origin. Okay, and so first question: explain the electric field at the origin. Why is the electric? What is the electric field at the origin? Explain it in words. Well, notice you have multiple charge. The same charge, multiple charges. They're the same value. So the electric field for this would be repelling in the middle with no field in the middle. So since the electric field lines repel in the middle, we have no net electric field in the middle. So that's kind of what it's getting at the first part. But what we're going to do here is we're going to go ahead and draw a field diagram for point P so we can get a sense of what we're going to do in this problem. So we want, notice the first charge, Q1, and Q2 are both positive, so they're going to be sending their field lines out in all directions. So I want a field that is directed up and to the right from point P, just like that. We'll call that E1. Then I want one that's directed up and to the left. That's going to be E2. Now we got to take both angles from 0. This angle here is going to be the 53.1 degrees. You get that because we are going essentially what? 2 over 1.5, and then we're taking the arctan of that. And then the other angle we're taking from 0, meaning 53 from 180. And again, it was, I forgot off the top of my head, 126.9, 126.9. Okay. Part 3, what is the magnitude and direction of the electric field due to the point charge at the negative side on the left? And then we're going to figure it out due to that on the right. Okay, remember the distance to each one is going to be 2.5. We calculated this earlier in part 1. Okay, we're going to go ahead and finish out this calculation here. For both point A, okay, and for point B, okay. And then what is the net field? Well, how are we going to figure out the net field? Well, first you have to figure out E in the X direction. That's going to be E1 cosine theta 1 plus E2 cosine theta 2. Figure out what E in the X component of your net E is. Okay, then you're going to do the exact same thing for EY, except all of your cosines get substituted for sines. Okay. Now, once you find that, to get the net field, you're going to use the Pythagorean theorem and add the sum of the squares, EX squared and EY squared. And that's going to give you your expected net electric field at point P. Okay. And then what you're going to do is you're going to replicate the situation by putting a 3 nanocoulomb charge 3 units away from the origin. That's 1.5 meters away from the origin. And then do the same thing with Q2, make them equal charges. And make sure you are placing your sensor at 2 meters, that's 4 boxes, directly above where the origin would be. Okay, you'll record your measured value for P. You will calculate your percent error. You will then figure out, using F equals QE, what would be the force on a proton. Remember, the charge of a proton is the elementary charge, same as an electron. And the charge on an oxygen ion, because it has two extra electrons, is 2e, right, which is 3.2 times 10 to the negative 19 coulombs. All right, so please take some time to go ahead and finish out your lab, okay? And I hope this tutorial was helpful.